So, good morning, everybody, to the last Friday of the semester. So, let me just check everyone in. Let me say that several people have contacted me about their final project topics. They sound very cool. I'm interested to see them. If you haven't done that, get those to me as soon as possible. I set or I'd been saying that kind of the deadline to get that to me was today. That was to get you thinking about it, but as a more stick versus carrot deadline, if I do not have a topic by the last day of class, you're not doing a presentation. Which would be extremely bad for your grade. So I encourage you to get those to me as soon as you can. As people have been contacting with me, there's typically a little back and forth to kind of figure out exactly what is a good topic. I've been trying to offer some suggestions. If people know that they want to do something involving, education or something in history or these topics, which are pretty broad, we kind of or everyone's been able to narrow it down and find something to talk about. So if you haven't done that yet, get in contact with me. Definitely hard deadline, last day of class. But as I said, sooner would be better. Also, so I'm just kind of checking everyone in here. Also, to say a little bit more about what I was expecting as far as the presentation, kind of what it actually can, not the subject matter, but kind of how you do it. The PowerPoint, there isn't a set number of slides or anything, just whatever you feel you need to give yourself enough material to talk about for the 8 to 10 minutes. So I would think, you're going to at least have 5 slides, and that would mean you talk for, 2 minutes-ish each slide. You could have more if you want to kind of show off a lot more, but there isn't a set number of slides, just whatever you think you need to put together an appropriate, a talk of an appropriate length. As far as how you make the recording, what I would say, or what I was thinking was, however you're accessing Zoom, you can create a meeting. When I look at my kind of Zoom app on my computer, there's a personal meeting ID, so I can always make a meeting. What I think could work well is if you make a meeting that is just you, record it and share. I guess you don't have to share the screen, but no, I guess you would. Yeah. So you need to share the screen, and that puts your slideshow or whatever visual aids you're using, that puts it on the screen, and you can do a voiceover kind of like a lot of these lectures. So I think that would work well before we get too close to the Monday of finals deadline for actually turning things in, it would be good to try it out and do a kind of sample recording to see that you can actually make it work with the technology that you have. And if it seems like there are issues in making that all work, let me know, and we can brainstorm some alternative ways for you to put a presentation together. But I think a solo meeting in Zoom where you share the screen and record it puts a lot of the things together. So with that, let me, okay. So what we were talking about last time, yeah, we'll look at this for a bit, is talking about, so we were making linear models, and that's just one example of how you actually come up with the model. We'd also talked about using software to generate lines that approximate data, but also a good question is, what do you, that's not what I want. What kind of questions can you answer? And there are a lot. Things can certainly be, you can try to gain a lot of insight about whatever phenomena, quantity you're measuring, but a couple basic things that you can use a model to ask and answer are, what is the quantity given by the model at a certain input? So if you're measuring something changing over time, what amount do you have after a week, a month, 5 days, something like that? Also, at what input does your quantity reach a certain threshold? So you were watching this quantity change, and when does it reach 100, whatever? So if you're watching a population, when does your population make it up to 500 or something like that? So here you're looking for a time or an input value at which the output takes a certain value. And then also you can ask, what's the long-term behavior of the quantity? So here, this is especially, or I'll say graphically, this is a question you can especially ask, because this is looking, maybe there's a lot going on in the near term, but often things sort of level out or have some kind of large scale behavior as you go, as you look further and further out for larger and larger inputs. So we're seeing what happens as you look far out on the graph. So the first question, and we talked about this last time, if you want to know the quantity at a certain input, that is, so you want to know what value does your model give you at a specific time. Mathematically, this is saying you're evaluating your model at a particular input. So this says take the formula Q, whatever that is, put in this input you're looking at. This will be some number. Q has variables in it. Replace all those variables with A. That's some number. Figure out what number that is. And that's the value that your model predicts at that particular input. If we're asking the second question, when does your quantity reach a certain threshold? So this is saying, this is a formula telling you for a particular input, here's the amount of whatever we're measuring. Here's the measurement that we're making at that time. So we want to know, when does the measurement that we make actually be, when is that measurement this value A we're interested in? And in that case, we know or we're saying the amount is equal to A, what time makes that happen? And mathematically, that is saying set your formula, which tells you the different quantities at different times, set that formula equal to this value A. You want to know when the quantity reaches that value, and that's an equation that you can solve. And so whatever, however the formula looks, you'll have to deal with solving that kind of equation. If this has, for instance, x's and x squareds, this is a quadratic equation, and then you could use potentially the quadratic formula. There's also plenty of software where you can feed it an equation and solve that, and that's especially useful if the numbers aren't especially nice or if it's really complicated. A lot of software can at least approximate a solution if there isn't any algebra we can do to solve that equation. The question we were talking about, so we ended with talking about the long-term behavior, which is saying given some model f of x, so this is the telling us the measurement that we're making at different times. What it means long-term behavior is let this input get larger and larger and larger and see what happens to the different measurements that you make at those times. Graphically, this is saying look further and further right on your graph and see what happens to that. And if it levels off, that is what terminology you've encountered before, that's a horizontal asymptote. So we looked at this example last time. We won't go through it in as much detail again, but if we have this quantity here, 2 over 0.1 t minus 20 squared plus 1, and this is easier to see if you write this as a fraction. My pen isn't very good, but so that's 0.1. Getting rough here. 0.1 t minus 20 squared plus 1. Okay. So this big fraction. If we graph this, oh my gosh, please go back. Okay. If we graph this, it has this kind of interesting shape here, which is kind of reasonable, or at least makes some sense if you think about it. If we describe what's happening here, we start pretty low. So t of 0 is, say, today. Then we start increasing at 20. We max out at, I didn't put the units in here, so maybe this is 200 people. And then we start decreasing. So from the graph, we can really describe what happens. We're starting low, but we're going to peak at day 20, and we can read off how high that is, depending on the units here. And then we're going to decrease. And not just decreasing, but we can say the long-term behavior is the number of hospitalizations is going to be 0. Because as we look further and further right out here, the graph is getting closer and closer to 0. Which also mathematically makes sense. If you think about, so you could do this with a specific set of numbers or just kind of think in general. If you take this fraction and you're putting bigger and bigger numbers in here, so like 100, 1,000, 10,000, this bottom part keeps getting bigger. So it's if you put in bigger numbers and square them, you're big. 0.1 and then times 0.1 and plus 1 changes a little bit, but if you make t bigger, this bottom part keeps getting bigger. And so as a fraction, the top is, or how we're computing this, is we're taking 2 and we keep dividing it by larger and larger numbers. And how fractions work is if the bottom gets bigger, if you divide by a larger number, your quantity gets smaller. And so it kind of makes sense that this shape or this function gives us this long-term behavior, this shape as we go further right, where the function gets closer and closer to 0. So from the graph, we can describe the near-term behavior, which is some of the more, in this case, saying from 0 to, we're starting low, we get up to 20, and then we decrease. But then the long-term behavior is, if you keep looking further and further out, what happens? And in this case, it's heading towards 0. Thinking about end behavior, and I should say these are not real data points, but they're some data points that I made up in situations which which kind of make sense as far as samples, hypothetical data points. So one thing that this end behavior aspect can help you with is to indicate how long is your model going to be useful. So for instance, if we have in a hospital the number of ICU beds over some number of weeks, it's going up and then going down, which as an infection peaks is maybe what you would expect to happen. This up and down shape fits well with this quadratic model here. So I used Excel to approximate these with a upside down parabola, this x squared shape. It fits things pretty well. And this r squared of 0.89 is fairly high. This value goes between 0 and 1, so it's pretty good. But what we can say is this does a pretty good job of approximating these points, so we can it would be reasonable to expect that we could use it to predict things a little bit longer. But what we want to watch out for is if you think about long-term behavior of this function, what's going to happen is, that was actually a fairly straight line. I'm surprised how well that went. At some point, this parabola is going to keep going down, and at some point it's going to be negative, which doesn't make any sense as far as number of ICU beds needed. So thinking about long-term behavior of your function can also say at some point this graph is going to be negative. So before that happens, I have to stop using this model. This stops being a good predictor of what's going to happen, because anything that says I'm going to use negative ICU beds just doesn't make any sense. And that doesn't mean it's not good kind of fitting in the points that we know. It does fairly well here. And that doesn't mean that it's not a good predictor maybe for week 9 here. But at some point, because we know this graph is going down, we have to stop using it. And being aware that this graph has limitations can let you know or have you looking for what happens when we get a little far out here. How do we have to rethink what the shape is going to look like? And so what you might think would be we need kind of a different model, which says maybe we need to say, this is the increasing phase, we're past that. We need to maybe think we need a model which looks, you might think, let's focus on these points, the decreasing part of our ICU bed need, and think we need a model which looks something like this. So that if we're focusing on the downward trend that we eventually get to, you can think we're going down and eventually we won't need very many ICU beds. Maybe we'll still need a couple because things don't completely go away, but we can think we want a graph that looks like this. So that says, once you figure out my graph is going to stop being good sometime, you can shift your window and look and say, let's focus on the new situation, which is we're in the downward trend. That means I want a different shape and I want some kind of lower bound, or I want things to be decreasing and but then level off. And how do I find a model for that? And similarly, in this number of hospitalizations graph, these data points I threw together, we can find a line for it, and that line is pretty good. You could maybe do better with another shape, but this line is already pretty good. And this suggests that things are going up. And if you keep extending this, you could reasonably say, or you could use it to estimate maybe what happens on input 5. But as you kind of overarching principle is you have some data points. As you extrapolate further, your model is going to get worse. So it's important to keep getting new points and then tweaking your model based on what those new points. So in reading a lot of coronavirus coverage, there are, a kind of a complaint, which isn't a real complaint, is, well, the models keep changing, the predictions keep changing. And duh, they better keep changing, because as we get more and more data, we can say, okay, now we have more information, which maybe says, which changes how we can make predictions. If you don't change your predictions based on no data, you're doing a really bad job. So if we started getting points that looked like this and this, you better not think, well, after 4 days, we made this model, which says we're going here. That's what we should keep doing. No, you can look at this and say, we have these new points, we need to adjust to those. And since while this part looks very linear, or a linear graph does a good job of fitting this, it doesn't work so well anymore. If we try to find a line fitting these points, it's not going to be very good. The R-squared would be a lot lower. So that makes you think, well, maybe I can't use a line anymore. I need to use some quadratic or exponential function, because now we're increasing slowly, but then we're increasing more and more. And so we want that change in steepness. But even if things kept going in this way, we know there's a limit to how good this can be, because, well, this line, if you just look at the graph, it keeps going up forever. And the number of hospitalizations is not going to go up forever. For more practical reasons like people developing immunity, developing vaccines or things like that, there's also just a finite number of people, and this line will eventually get to be 10 billion, and there cannot be 10 billion hospitalizations because there just literally are not enough people. So as you get far out, you might want to change things because the data changes, but also there's a limit to how many hospitalizations there can reasonably be just because like number of people issues. So thinking about long-term behavior can help you know when you need to adjust your model or stop using it in favor of something else. As a last pretty interesting example of end behavior, there's what's called a logistic growth function. So we'll see the formula that gives us this shape, but this kind of logistic growth is really good at talking about quantities that are fairly stable or pretty low, increase fairly rapidly, and then level off again. So an example would be if you have a new species introduced to some environment, especially if that species is invasive and doesn't have predators, it's going to increase really quickly. But then you run into issues like carrying capacity or kind of human intervention or something that limits its population size. And so when you're close to the upper limit, there's some cap on how big you can get. This keeps growing, but it stops growing as fast. So this logistic growth function, the end behavior, it naturally has this upper bound, and that's its this horizontal asymptote of 4 in this case. This also works in kind of the same way for the spread of disease, in the sense that the virus is a new species and the habitat is people. It's fairly low, it increases, but at some point it stops being able to increase as fast because there are caps on how fast it can keep growing. Because I mean, the whole idea of the term herd immunity is if 95% of the people are immune, even if someone gets sick, there aren't enough people around that aren't immune for that disease to spread. If you have 100 people and one of them is sick and 95 are immune, it'll be really hard for that one sick person to find the other 4 people they might give the disease to. And it's especially hard when you consider that there's a limited time for them to actually find them. You can only give it to them while you're infectious, and if it takes too long for you to find one of the other people that isn't immune yet, then the virus loses. So as you get close to this cap, it stops being able to grow as quickly, although it could keep growing because there are still people that are susceptible and that can keep getting the disease, but it's not going through this rapid increase phase in the middle. So this logistic growth function, which one are you here? This one. zoom in. So the basic version is 1/1 plus e to the minus x. This e is this irrational number, 2.718281828. And you don't have to use e here. If you want, you could use you could use another number, but e and exponential functions involving e are especially important in calculus, so it's kind of standard to just use this number e. But there's nothing especially important. You could use other numbers there. So this is the basic form. It has this horizontal asymptote of 1, and here it has this increasing phase in the middle, but then it levels off. It also levels off if you go backwards. So this is the basic form of these logistic growth functions. What you can do with them, though, is like we did last time, there are some parameters you can play with. Parameters meaning you can change the numbers. So these two examples have different numbers in different places. And if you change those, that lets you have this same general shape, but maybe fit different types of data. So in this case, this 10 and this 5 here. So what the -5 does is it makes things steeper. And so depending on how steep you want it to be, you can just -x is pretty flat, -5x is steep. If you want things to be super fast, you can put in like 50. This is basically vertical. So this is something like, I don't know, if there's some incredibly viral meme, viral, that might be a less, people might stop using that in the same way. But if you have some incredibly viral meme, it goes something like, no one has seen it, tons of people see it, and then basically everyone has seen it. So depending on how steep you want this jump to be, that can reflect how quickly whatever this is spreads. There's 10 here, so you can put an extra number here. That lets you shift when the increasing stage happens. So if we put on 100,000, so we can keep pushing this number out to change when the increase actually happens. Or another way is x minus 4, 3. So there are ways of shifting when that increase happens. You can also shift how steep it is. So we're this third case also, let's zoom out a little bit. Other tweaks you can make, this -0.4 makes things flatter, and this 3 changes how high you actually go. So both of these had a 1 on top, which meant that they both leveled off at 1. One got there faster, or I guess they kind of get there close to the same time, but this one's a longer, and this one's just really fast. You can also change how high you want that leveling off thing to be. So these logistic growth curves, you can say, I know my behavior, or so I know that my quantity has these characteristics and will look like this, but you can change different aspects of that same type of function to fit exactly what's happening. So for instance, if we say, if we look at these two graphs, this could be an instance of maybe, if we think of these graphs as saying what percentage of the population has gotten infected by the COVID-19, they both say basically everyone's going to get infected. But one of them says it's a very fast transition. The other one says we get there, but this is a lot slower. And so this red one is more like we successfully flattened the curve. The point of social distancing is not to say, like, we can't just stay inside until there's a vaccine. But if we can spread it out more, then there's no point where we need way more resources than we have to handle it. Just kind of where people are steadily increasing, we're having more and more cases, but as more people are infected, more people are getting out of the hospital and recovering, and so we have the resources for the new cases. And so these both have the same kind of long-term behavior, but we can change their short-term behavior, and we can use them as comparisons to see what these compare these two possibilities. So what I want to give you today is a problem for you to try. So let you guys try it for a little bit, and then I'll come back and I'll talk about some of these. And there's a quiz that's on, or a kind of in-class assignment on Canvas, but we'll say for now that I'll give you guys a few minutes. Actually, let me, okay. So how do you guys look at this for a little bit? And you don't have to do it now. There's nothing to turn in. The assignment is turned in sometime today. But think about what you would have to do to answer these questions. So what to focus on is the stock market isn't doing well, but it's going to bounce back. An economist comes up with a prediction to say that the index in thousands over the next 2 months is given by this parabola whose graph is over here. And this is the wrong kind of bits. So a couple questions that we can ask, both using the formula and using the graph, are here. So take a few minutes and think about how you would answer these. And you don't have to answer them right now, but think about them, and then we can come back and talk about how they're going to work. So I'm going to step away for a little bit and let you guys look at these problems and thinking about them, and then we'll talk in a sec. Okay, so that's just a little time for you to think about this. So again, there is a short quiz on this on Canvas. Make sure you do that. But what are you actually looking for? So each of these, we want to think, what mathematical question will get us this answer? So what does the model say the value of the stock market is right now? So right now is, or kind of, and often now the initial quantity on what you're starting with, this is saying figure out the stock market at 0. So there's some point here where t equals 0, what some point we get on this purple parabola for that, that's the number that we're looking for. And from the graph, it's not clear what that is. And this 1.3 makes things so it's tough to just eyeball and do by hand. Right, and so it's not a quiz, it is an assignment. Oh my God, it's, all right, so, nope, that's not it. Okay, cool, found it. So this S of 0 is hanging out there. Right. Stock market model questions. Okay. So for this one, the initial value is wanting to know a specific output at an output at a specific time. In this case, we're not given the number, but we interpret now, especially since we're saying t months from now is what the input is. That's the value we're looking for. The lowest value of the stock market and when it occurs, from the graph, we can figure out, so there's a dip and then we go up. We want to figure out where that dip is and where it occurs. This we can find from the graph. Right there. It is worth pointing out that finding this mathematically is one of the primary tools of calculus. It takes a little bit of building it up, but it's one of the first sort of applications of calculus that you really encounter, if you were to encounter calculus. Question 3, so how long months will it take, according to this model, for the market to make it back to 25,000? So in this case here, this is asking a threshold question. When, so at what t value will our stock market make it up to this? And so here, this type of question means set up an equation. And so we want to know when is S of t equal to, and what we enter is 25. So keeping track of the units here, the stock market index in thousands. So 25,000 would correspond to an output of 25 from our model. So you don't want to set this equal to 25,000 because that would mean you're actually figuring out when the stock market is 25 million, and that'll be in a long time. But if we look at this graph, 25 is right about the cap here, and that happens not too far out. So we can see that somewhere in the not too distant future, or some number of months, we make it back to that level. And the last question is saying you can compute all these values, but you also want to be able to kind of make a prediction using words. So in words, you'd say we're starting up here, we bottom out at some value at some time, and then we start increasing again, making it to 25 at some time, but then we keep going up. And wanting to find a model for the stock market is definitely worthwhile, because if we look at the Dow Jones, so this was the big financial crisis of 2008, 2009, and we increased. And then this is us, a big dip again. So what would be really hard would be finding a nice smooth function which exactly fits this, because it's really like every day it jumps a lot. And so there's not a nice function which exactly fits everything. That would just be incredibly complicated. But what we can maybe say, and here's an example of using one of these models, is if you look at this part right here, kind of post the bottom out and before our current situation, this is pretty linear. So while it's obviously not perfect, we're higher, lower, I mean, lots of jumps all around, you could predict, as long as things kept going like they have been, we would expect us to be up here. And obviously things have not gone the way that people predicted, but a lot of models are given the information, we try to assume that if things keep going the way they are, then we can look a little bit further in the future. It is tough to account for really sudden things, but even this drop that happened in kind of late 2015, that still came up and we were still pretty close to this approximating line. Okay. So make sure that you go through this assignment. What I also posted was I posted a homework 7, and what I'm going to do, this is the making a trend line model. And really quickly, I just want to point things out, and I'll make a longer recording, but in here, there is a website, which is Georgia census data. If you click on this county population file, you get a big county spreadsheet like this. And what the assignment says is pick the county closest or alphabetically to your last name, and you're going to model that population data. So you're going to say, I took Clark County, which is where I live in Athens. Also, it is not alphabetically closest to anyone's last name, so I knew it was safe. Take those data points, turn them into a table, make a graph, and then put in these trend lines. So I'm going to make a recording of me walking through doing this example for Clark County, and you guys will try it and answer a few questions with the county who's closest to your last name. So watch out for that video to get posted, and make sure that you do the in-class activity today. But other than that, let me know about those projects as soon as you can. Um, and have a good weekend. And I'll see you guys on Monday.